Okay, good morning, everyone. My name is Marcus Boerger, and welcome to Production Proven Practical Constexpr API Elements, or some order of those words. And I am from Switzerland, where skiing is just much better. So now we're dealing skiing. All right. What are we going to do today? We will get some introduction to the topic, some basics for everything. I'll show you a hash function, how it works, why it works, what it does, what it doesn't do. Then I'll talk a bit about objects, and then I'll talk about a few containers. Then I give you a glimpse into production and metrics we encountered. And yeah, the goal is to learn a bit about Constexpr and what to do with this kind of stuff in compile time and runtime. And by all means, feel free to interrupt me at any point in time. I'm more than happy to at least try to answer some of the questions you may have. There are far too many slides. If I talk too slow, let me know and I skip. And I may have to skip some slides anyway. We'll see how that works. Okay, how do we do this? There are a lot of, guess what, code slides. I'll distribute the slides later. Some of them have this green icon. Who knows what the green icon is? I guess everyone by now. Compiler Explorer. So those slides have exactly the same code for Compiler Explorer so that you can experiment with that. And then the ones with the other icon, that's an icon someone made for my web page. I guess every web page has to have some icons and stuff. So I had zero impact on this. I think it's kind of cute anyway. The more complex stuff that isn't like, like really weird construed to demonstrate how something works, they're all production proven stuff. So most of the slides are actually code we run in production. Okay, so where is this stuff? You can look at it if you want. It's published on GitHub. I have a web page where, unlike some people, I think there's Jason in the back who, how often do you publish stuff? Like continuously, kind of feels like. I can't be bothered with that, or maybe I just don't have any time for that. License is Apache 2.0. It's used in production. It's built using Bazel because I still can't get my head around getting the time to do it also in Snyk. If someone of you wants to do it, be my guest. Who am I? I spend some time in production laboratory automation. I spend time in automotive research. I spent 16 years at Google. You might use one of the products I owned, Google Public Transport. And now I'm at Snyk, where I do, well, again, tooling, automation, and otherwise, for real, we do static program analysis. Yes, once upon a time, we were young and naive, and we needed the money. And we celebrated that some compilers optimized strlen. Everyone remember this? We were happy that you wrote strlen and nothing happened. And we were so lucky to have this. Well, it only worked sometimes. And it was clear when it happened and when not, if you understood what the rules actually were for this. Then came along C++11 and we had Constexpr. And it was amazing and largely lame and pretty useless. And then came C++14, and they fixed a lot of things in C++11, and we had better Constexpr, and it was lame and still useless. And then came C++17, and it had better Constexpr, and you could finally do amazing, crazy stuff like Constexpr standard string view name. Oh my God, isn't this amazing? You can actually get access to the length of your string in literally forms. It has a name even. Fantastic. Well, yeah. At that time, I was working on one of Google's core libraries. It runs on every system Google has, every piece of hardware. And we optimize it. So I thought like const expression, let's write a hash function. How far do you think I got? 2 weeks into suffering and then deciding what is the best solution to any problem you might have in our industry. What's the best solution to any problem?
Use someone else's code.
No, to not have the problem to begin with. So if the problem is creating the hash function because that's too slow, then you shouldn't be creating the hash function, which is the whole point of const expression. So instead, I wrote a library that takes the code and pre-computes the hash values, puts the hash values in, and then a test that verifies that you didn't screw it up. So we couldn't do const expression, but we could do it with weird tooling. All right. Still lame. C++20 to the rescue. Things are getting really interesting. And as you can see, I can finally do a hash function. 23 even better. However, it's painful to upgrade from a real code base from 20 to 23. It's like massive amounts of work. Yeah, and there are actually some things when it comes to const expression that I really don't like that they did in 23. Maybe we get to that point too. The basics. A const expression initialization is a const at compile time. Make sense? So when you have something that has const expression on the left and you assign to it, that shall happen at compile time. So far with me? That's the easy part. Okay. In technical terms, a literal type that is immediately initialized through a const expression. So something the compiler handled, that's easy enough for it to understand, hence literal type. We see a bit about that. A const expression function is one that may, favorite work of this talk, may be executed at compile time. And it's really complicated. And we probably don't have enough time to go over all of this. Okay, a const eval function is a function that, if you were in JSON stock, you should know about this already. It's basically, unlike const expression that is may, const eval says either it is done by the compiler or it's a failure. Right? So that's the short one. All right, and then there's const init, and a const initialization guarantee comes with it, meaning the compiler will ensure that whatever you do with const init on the left side is initialized at compile time. So far with me? Okay, now for the hilariousness. A const expression function requires the return value and the parameters must be a literal type until 23. Okay, what is a literal? Who knows what a literal type is?
Little string, little reds.
No. Well, they are also literal types, sure. But it's a bit more complicated. So a literal type is a void, a const void, or whatever, a scalar, a reference, an array of literal type. Okay, so far so good. All right. Or an object with trivial const expression destructor. The trivial is only necessary until 20. And starting with 20, it has to be const expression. All right, so let's put an asterisk there. And that is one of a lambda type. Okay, lambda type is easy, I can deal with that. An aggregate union without variant members unless there is a non-volatile literal type. Does that still make sense? So it's a union, and it's a strange union or whatever. The only thing you can't do is, for the purpose of easiness, don't do variants in unions. Right? So that's the easier form than this. An aggregate struct where each anonymous member is not a variant. Well, that's easy. Don't do anonymous members in structs anyway. They are annoying. So, okay, so it's an aggregate, and it probably shouldn't have a variant member. A type with a one actual const expression constructor that is not a copy or move constructor. So a real constructor that may be working at compile time. Again, may. Well, it doesn't have to, may. In technical terms in C++, I think it says at some point there must be one condition where it actually would provide a compile time executable version. If that doesn't exist, it's a failure. In 23, they removed this, which is sucky, because then in 23, the compiler no longer tells you if there is no way how this can be a const expression. So that's the big annoying part there. All right, for methods, let's skip to the chase. Basically, it means the class cannot have virtual base classes. Well, if you use virtual base classes, you probably have a tendency to shoot yourself in the foot anyway, so let's hope you're not doing this. For parameters, until 23, so this is the other annoying part, there exists a set of arguments, so this is again like this maybe thing and this condition, where this actually does work out to a const expression. And for constructors, you can prove this by using them in a constant initialization. So when you have an object and it has a const constructor, when you can assign this to a static const expression, well, then obviously it was a const expression, right? And because of that, they decided that no diagnostic is required for a violation of this bullet. And that's the annoying part about C++ 23. You no longer get any interesting warnings that help you develop the code. All right. Yes, no diagnostics, really annoying. So for the time being, I apparently stick to C++ 20. It's too much work anyway. And, well, this goes on and on and on. So this was only like a very, very short version of the conditions for const expression, but I eventually get the hang of it. And eventually you cut all of this down and keep only a few things in mind. And yes, C++ is awesome. It has only a few problems. The standard at the moment, the C++ 20 standard, is nearly 2,000 pages. 23 will be over 2,000 pages, I think 2,100 or something. And it's already like 6.7 megabytes. That's insane. And we haven't even touched any API you wrote for your systems or any of your actual code you work with. We haven't touched any of this. No tooling, no nothing. It's already like 2,000 pages. Like, who's going to learn this? Like, if you grew up with it, you know, C++ from day one, then that may be fine. But if you nowadays start, it's really annoying. How can you deal with that? The one thing you want to know, test everything. Try out everything. Use debuggers, whatever you want, logging, whatever you want. Test everything. Yes, test everything. If you want to take one thing away from any of my talks, test everything. There you go. Let's do some silly stuff. We talked about the super silly. You can do const expression string view, and you should no longer do blah blah const expression, whatever, and then a char pointer or a char array. Don't do this, just use string view. More silly stuff. Okay, what do we have here? We have a function twice that is const expression, and it just multiplies the input by 2. And as we said, this means maybe it's a const expression, maybe it's not. And then there's a const eval triple that multiplies by 3, and that is enforced to be at compile time. So that requires, obviously, that the argument qualifies for being const expression handleable. And if you remember on the earlier slide, it basically means it must be a literal type. So if you give it an integer value and you pass it in, that will perfectly fine. If you give it something more complex and the compiler has to convert it, it probably doesn't work. All right, next one, foo is a volatile. Well, the volatile is obviously the keyword, the easiest keyword to see. This absolutely prevents compile time, because obviously volatile means always execute no matter what. No caching, no nothing, no optimization, no nothing, always execute. So obviously can't be done at compile time. All right, so then we have a main function here. And the first thing we do is we initialize to const init a variable x, which is twice 8. Compile time or not compile time? Anyone? It's compile time, because const init enforces that it needs to be able to be at compile time, so we hope the compiler can do it. All right, the next line, static const init y from foo, which is our volatile function. Well, the compiler won't like it because there is no way how the compiler can use foo to construct something at compile time, so it's an error. The next line, static const expression z triple 4 works fine. Difference here is we have an actual static constant that stays constant for its lifetime. And then we have the next thing, an integer at runtime, 3 is triple z. Well, so triple, does this work? Yes, because the initialization happens at compile time. So 3 is initialized just as if we have written const init, but then you have a value that you can happily operate with at runtime. Okay? And then we do return x, y twice foo. What's the answer? Anyone? No one has computed this? It's 42. It's always 42. All right. Okay, so here is the output when you look into the debugger, or in this case, I actually use Compiler Explorer. I really love Matt's work. It's fantastic. So you got the assembler instructions. And you see it created as expected the function foo. And it has the main function. And this is in O1, so that it skips out a lot of the unnecessary fluff, because it actually in O0 generates much more code because of the maybe. Right? It doesn't have to do it. So it generates more. In O1, it optimizes all of this out. But we don't get better. All right, let's change this. So here we have the stuff as before. We change our foo to be a const expression function. We remove the volatile, so now this can be run at compile time. We change our initialization for the x into a static const expression. The z is a const expression. And we just return the xyz doesn't work, it's runtime. So we actually have to store the result we compute into a static const expression variable, because that's the only way to prove its compile time. And otherwise, the maybe goes into effect, and the compiler may or may not actually do compile time. So by assigning the result we want to a static const expression, it's enforced its compile time. And then we can return the R. So then, as expected, in O0, we got the one main function, nothing else left. And in O1, it removes the fluff that no one needs from their functions other than for debugging. All right. Next thing. We can change a lambda. So lambdas are getting more and more popular. So you can see here, I didn't actually change the return statement. So I just wrapped the return statement into a lambda, and I allow the binding. And so these are const expressions, so they are compile time, so they can happily be bound. And then I mark the lambda as a const eval. So obviously, what you can do to a normal function, you can do with a lambda. So here it's a const eval. So I know it's guaranteed this is compile time. Right? And then we can change something. We can do the functions in const eval. And well, do everything in const eval obviously works. So now we have proof that it does work, because we write it works. The compiler will just fail if it can't do what we ask it to. All right. So how do we actually know that maybe translates into compile time after seeing this? Can we actually know its compile time? The only way to know its compile time is to use const init, which afterwards allows us to use the stuff at runtime, or to do something and assign it to a static const expression. Those are the only ways. Everything else is up for the compiler to decide what to do. So you can fiddle as much as you want with O0 or O1 or O2. You will never figure out what this thing actually will be tomorrow with the next version of the compiler. They constantly improve. Plus, just because you don't see a function, does that mean it was compile time? It's a catch question. That, you compile your code and you look in the debugger, the function isn't there. Does that mean the compiler chose compile time execution for that function? No. Why?
It could be inlined.
Exactly. It could be inlined, or it could be just optimized out. The compiler could have found like there's no point in executing this. I know the answer to this, right? So then why execute? It has nothing to do with compile time. Those are different things. So yes, short answer is you can't unless you do the correct assignments. All right, here's a hash function. This is a very weird squished together hash function actually used somewhere in production. And you see it has a bunch of things. You see it has a bunch of mem copies. Why would it have mem copies here? Turns out the mem copies are faster. This one chooses to only do 4 bytes, even though it has an 8-byte return value. It does so because it tries to limit the amount of collisions while still being as super cheap as possible. So this is a super cheap hash function, and it tries to do something to limit collisions. Well, if you can, you probably shouldn't use something like that. They are still too silly, and there are much better options. Okay. Let's write inline Constexpr. Why inline? Because Constexpr, in order to make this available throughout your code, you probably have to move it to the header, and then you have to write inline, of course. Okay, so does this work? Take a guess. Who's for, yay, does work? Who's for, nah, does not work? All right, you guys are right, does not work. It doesn't work because it has the pesky mem copy, which turns out to be not Constexpr. Therefore, you can't use it. Makes sense because it fiddles with memory at runtime, so why should this work at compile time? All right, but we can write this differently. However, now, this works perfectly fine. We can do this. We could even write const eval, and the compiler will tell us this works perfectly fine. But it's shit, because if I use the same function at runtime, what do I get? Like an order of roughly 1 magnitude slower than before. So I probably shouldn't. But how can I do with my favorite solution of not having the problem to begin with? That was the whole point of Constexpr, to not have the problem, to not have to compile the hash function. Well, let's look at this. We have a one version that can do it fast at runtime, and we have another version that is shitty slow, but it doesn't matter. It can do it at compile time. All right, let's go back to Constexpr. And now we do the following. We have a one namespace, compile time, and the compile time has the hash function, and then, well, slower one, but that happens to be Constexpr. And we have the other namespace, runtime. And then we have a inline Constexpr, same name, different namespace, and it does this amazing thing. I hope everyone can see this. Is constant evaluated. So is constant evaluated knows in the condition whether this is compile time or runtime. So because we have this, well, we do is constant evaluated and then compile time version, otherwise we use the other version. So now the function decides by itself. We will never know what it does, but it will always do the most optimal form, either not do anything or do it at runtime. Who has seen if Constexpr? Okay, can I write if Constexpr here? Anyone? Aside from Jason, I'm sure he knows the answer. Can I write if Constexpr is constant evaluated?
Yes.
I can, yes, I can always, but it's pointless. If I write if Constexpr is constant evaluated, the answer to this will always be true, even for runtime, and then it won't compile anymore because then you try to do stuff that simply don't work, right? No, so this is like a weird thing. The answer to is constant evaluated in a Constexpr statement is always true, and that is because the concept is a thing that works at compile time, so therefore the answer must be true, right? So no Constexpr here. All right, objects. Objects can be constructed at compile time. Yay, and we've seen there were some restrictions. Here's an example. We have a struct test has a const eval constructor, and we set it to default. Because we set it to default, we actually don't have to write the const eval. Should we write const eval anyway? Yeah, why would you write it anyway?
Is that what you did if you messed it up?
Yes, you know whether you mess it up, plus you can show intent. You can show that I really want this thing to be done at compile time. And then we can do all of the other stuff like static init, test, blah, 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 blah. And because this is a const eval constructor thing, we don't have to do something special about the destructor, and we can do funky stuff in the destructor as much as we want. Because here we only say it will be constructed at compile time, and we don't worry about the rest of the lifetime. That can be, just as normal stuff. All right, next thing. Let's make them const expression. If you make the constructor const expression, well, same as before, you can drop const expression, or you can say, I really want this. And it's a maybe, so writing const expression, if it's allowed, doesn't hurt anyway. So now we also, however, we read this earlier, we have to make the destructor also const expression. And because it's a const expression, we can no longer do funky stuff. Basically, it means we can no longer have side effects. So things like printing, logging, none of this are allowed anymore. All right. And, well, we can write a const expression, test, works perfectly fine. All right. Next one. Const eval constructor, const expression destructor, same rules as before. You may or may not write it. Why does this work? Well, whether we enforce compile time construction or allow compile time instruction doesn't matter. We can still say we also may allow or may hope we get compile time destruction, right? So this one also works. And then you can do the things with static const init, or you can do const expression. Right. So I do static const init test, but const expression test. What's the difference? Anyone? It's a lifetime difference. The static const init means, well, this is static, I assign it, and then you leave it there, and it has a constant expression. So at some point, I no longer care whether it actually executes the constructor or not. Well, if it didn't execute the constructor at the end of the program time, do I care? No, why would I care about that, right? The const expression test that doesn't have static will definitely run the destructor. But the destructor here is a trivial constructor, so what does it do? It will do nothing. It will just like know that, well, at some point I may or may not have called the destructor, but I'm happy with that outcome. Okay, but this talk is about const expression, so yay, no more const eval and const init. I find them confusing, plus the topic was anyway a mixture of compile time and runtime, so only const expression. And let's take it up a notch. Containers. Let's store some stuff at compile time, maybe. All right. Containers need space for the objects they store. No matter what you store, it has to go somewhere. A empty struct or union in C++, how many bytes do you need? Anyone? 1. Okay. An empty struct or union in C, how many bytes do you need? Well, 0. Right, there's a difference between the two languages. All right, C++20 does not allow static variables and const expression functions. It's a C++23 thing. I really hated this one thing. I would have loved to use 23, but then I knew about all of the other things that come with 23, and I'm happy I did this in 20. All right. We still need space for the objects to go somewhere. We couldn't do all of this memory stuff. You can assume that all functions that deal with memory, they are all non-const expression. New and delete, there are some crazy ways where you may or may not be able to use them. I don't like it, so let's not go there. We still need a scratch space. We could switch to allocated memory at runtime to make this more interesting for the actual runtime versions of the containers. I'm not talking about this, plus I'm far too lazy to implement it anyway. All right. Hello? There we go. Standard array, the first const expression container that fully works. Interface is roughly like you give it a type and a size, and it has an implicit constructor and destructor. It can do crazy stuff, and they all suck. So the one thing you want to know, there's a helper function coming along in 20 that does that's named to_array, and that allows you to take your list of values and show it into the array, and then you have the correct array size. Let's look at this pesky thing called size. So here we have an example. creates a standard array, and the standard array has a bunch of elements. Who knows how many elements there are? Not counting. There are 11. There are 11 lines in London, so there are 11, okay? But I have this silly thing, I wrote 20. So I have an array with 20 slots, and I give it 11 string views. What does the compiler do? Yes, so it actually gives you 20 elements, so the function will return 20, and you just get empty elements, and they are default initialized. Since it's a, well, string view, what do you get? You get something that potentially is a null pointer and a null value for the size or something. They changed this a few times between the original Google version and the later versions that they put into the standard, and they fixed the mess they created at some point. Anyway, so you get a default initialized thing that says the size is 0. That's the only thing that you actually get out of it. All right, let's look at what size does have. I mentioned there is the toArray thing. So here's the toArray thing. So then I can do Constexpr out of lines, toArray, and then my list. And so finally, yay, the program returns 11. And there we go. That's the O1 result of this program. There's nothing left of the lines or something. Computed everything at compile time and just says 11, end of story. That's it. All right. Standard array is a bit inflexible, and yay. And there's toArray. It still sucks, and you can't do too much with it. So I wanted to fix some stuff we have, so I started writing code. All right. I said we need scratch space. How do you get memory at compile time? Preferably initialized memory. Why would I care for uninitialized memory? Isn't this sucky? Like, aren't there things like asan and msan and ubsan that will tell you off for doing this? Yes. Why? Because initialized memory is what standard array does, and you got default initialization. And that's something I don't want. Now, technically speaking, at compile time, I wouldn't care. So if this was only for compile time, I would say, well, whatever, like I can do with whatever. I can use a standard array and get default initialization, doesn't matter. But this is a mixture of compile time and runtime. So whenever this is used at runtime, I really do not want to have anything initialized because it costs runtime. So I want uninitialized memory. All right, uninitialized memory. How do we do this? There are a few more things here. I'll talk a bit more later. The one key thing is I hold myself and everything that comes now to be as close as possible to the STL as I can, right? Because I want to be able to, at some point in the code, replace all of the containers with the containers we are developing here, and see how much it buys me. Well, obviously, I only do this in the area that have a chance to be compile time, but I also need to have these things compatible, because if I don't make them compatible, I have to do with ranges or with views, or I have to write my own wrapper, I have to write silly code, and then I get code blow up because suddenly I have to have polymorphism for every function that deals with any data, and I can't have any of this. So as compatible as possible. Plus, how can I convince my colleagues to use any of that if it has different interfaces? Answer is I would never be able to do that. So it needs to be as close to 100% compatible as possible. All right, here's the scratch base. A union, don't you all love unions? So this union has a Constexpr constructor, and it's defaulted. And we write Constexpr because we want to convince the compiler that we want to do this at compile time. It has a tag, none, which is empty. So as mentioned, we have now at least 1 byte. Doesn't matter because any other object will also have at least 1 byte. So no matter what I want to store, this none thing doesn't do anything. So it's a weird thing, but it's none because we never do anything with it. And then it has the T, which is the data. And we tell the compiler that we would like the compiler to think this union by default is a none. So the none has nothing to initialize, so therefore we get a memory that ASON will happily put something in that it makes it happy to understand that it came from the none, and we don't care. At optimized form, the compiler will simply don't do anything because there is no one who tell the compiler what to do this one byte, right? So nothing is happening, and we can technically use this because it's a union with our data. So there you go, uninitialized memory. All right, here's a scratch space a bit bigger because there are pesky things, and it starts with destructors, and it starts with the rule of 530. Anyone knows the rule of 530? Everyone? Okay, good. So let's not go there. So turns out I have to write all of the stuff. I have to write copy assignment, copy constructor, move, all of the stuff. So the whole thing got a bit larger, still does exactly the same thing as before, but now the compiler is happy and convinced because I wrote const expression and no except for all of these. So now we actually have working stuff. Now we need a little bit more because turns out there were these rules, destructors at compile time required to be trivially destructible. So therefore I have a version that is trivially constructible and one that is non-trivially constructible, and one can be defaulted and the other can not be defaulted. And so is this slide correct, and should I write this code as is? Good question. Does the compiler like it, and should I write it like this? No. Yes, I shouldn't. What would you change?
You're never calling. No, I don't. Never mind. Go ahead.
All right, so the first destructor says for any type that is trivially destructible, do whatever you like. Because it's trivial, the compiler probably decides to not do anything with it, right? And the second one says, if this is non-trivial destructor, then I tell you to not do anything. And it's Constexpr. So, but the rule is that if it's not trivially destructible, the destructor can't be executed. So now there's a weird thing where as long as the compiler thinks this is a none, the compiler will be happy. So therefore, I'm allowed to write Constexpr here. I probably shouldn't write Constexpr because this thing can never be used at compile time. So it doesn't really matter whether I write it or not. But here's the thing. By writing Constexpr should at some point, because it's allowed here, right? There's nothing telling me off, because there is a way how this could actually be executed at compile time, in theory, technically, because it actually doesn't call the pesky destructor, right? It doesn't, because we didn't default it, so it doesn't call it, right? So that allows me to write Constexpr, and maybe in the future, and God knows what, like C++30 or whatever, this suddenly starts working, right?
Today, you can't have something that is Constexpr destructible, but it's also not trivially destructible. So in that case, you would want to manually call the destructor data in your destructor review.
Yeah. Technically, you are completely right, but we use this only as our scratch space, meaning the actual constructor and destructor is called somewhere else anyway. So here it's just about preventing the compiler from doing something I don't want the compiler to do. All right, so library, okay. At a glance, where is this used? We do something data log, which is a triple storage that you can heavily query and has some optimized data structures for this. And then we have a large schema, and the schema produces a lot of those triplets, and they need to be stored somewhere in vectors. Some of them must be searchable, so you get sets and maps of all kinds of stuff. And because we have a schema, all of this is known way before we even think about any compiler. So we actually generate the code And so this got me to, let's see what I can get when I actually turn all of this actually from stupid runtime initialization of these things into actual compile time. And I do a bit more optimization. We see some of this later. So the code affects roughly 33% of the runtime of the application. And the overall improvement by doing so is 1%. So should I have done this or not? I typically tell people if you don't get more than 2%, you shouldn't be doing it. So should I have done it or not? Well, I affected only 1/3. So technically I have to multiply this by 3. So I actually gained 3%. So yay, I barely managed to get over my 2% rule. All right. First container is a limited vector. I think you had the question. I also find this naming stuff annoying. We already had a small vector and a gazillion of other things. So I decided limited it is because it has a limited space. It's like you once set it and that's the end of the story. All right, so then there's a limited set and there's a limited map, and they are compatible to their namesakes as close as possible, or as close I could be bothered. There is one function missing. They have no allocators. Reservation for the maximum is happening at compile time. They use uninitialized memory. They have optional destructor suppression. So sometimes when you do this static stuff, you don't want the compiler to think about destructors. You really don't want them. And since we already have uninitialized memory where we have to call the destructors elsewhere anyway, we may as well why not just don't call the destructors anyway. It doesn't matter because it will live throughout the program life anyway. It's not even an ASUN or MSUN or any memory leak or anything because it's perfectly valid, because it's static initialization, doesn't count for memory leaks. All right. One funny thing about the vector, it actually needs a sentinel element. I tried for about a week. I couldn't convince ASUN to accept the vector implementation without a stupid, silly additional element at the end. Was insisting there is some piece of code that I still don't know where ASUN thinks there's a piece of code that accesses that element end. It thinks so. It doesn't, but who knows? Well, adding one element probably is not too costly. Doesn't matter. All right, so here we go. Limited vector. Well, it's a final class. It takes, well, like an array, so it also has like similarities with arrays, so it takes the type and the capacity. And then, you have the none, the data, and at some point you have size, and you have the values, and the values are an array. Why array? Because I first tried to use things like, it's like C++20, so you use an array. Doesn't work. ASUN really doesn't like doing this with standard arrays. So back to telling Klang tidy that this has an exception and it needs a actual array. And there's the +1 to make the other part of ASUN happy. All right, so now let's take this up a notch, because I was talking about destructor suppression. There are a few more things you can do. So who has seen template blah 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 auto something? So the auto means any type and then a value. So it's not a type you're getting, it takes any type and a value of that type. So it means it will accept something like a size t, and so I can still throw in my actual capacity there, but it will also allow other things. And that's how we get the flex then later in. And so let's see, mixed auto template arguments. So all right, so I have my auto capacity or options, right? And so that means I intend to either give it a number or something that can produce a number, or an object that can hold possibly the size or something else. So I need to have a few checks on this. So here's my requires line. And I say, whatever I get needs to be convertible to a size t, or alternatively, it should be possibly the type that I want for my capacity or options. So there's a type capacity or options that can handle the size and the options. Why do I do this? The current implementation doesn't have allocators, but there's nothing wrong with adding allocators later. So if I were to now put the options already in some weird places, I would need to think of how I want to do it, and I get incompatible with the template invocation. So it's like, no, screw this. In most cases, people will only put the size there, and I get a limited, a much smaller API divergence by doing it this way. All right, let's move on. So now I have something that I know is either my object that holds the size and some flags, or it's actually the size. So does this work, the yellow code? Does it work or not? Obviously, I wouldn't ask if it did work. It doesn't work. But why does it not work? It doesn't work because what I have is either a size. Well, a size doesn't have a dot capacity. Or it's something that is an object, but that object can't be converted into a size because that's what I assigned to. So no matter what I do, there's no way the compiler could produce code for this. Even though we know, well, the compiler should know how this is, but a ternary is not a Constexpr thing, so it doesn't work. All right, so we have to do it differently. Compiler error, here's the explanation. So, much easier. We just make our options compatible with size or itself. So all we have to do is we have to give it a constructor that takes just the size, or we have to allow the copy constructor, at which point, no matter what our auto template parameter is, now constructs an options thing that I can assign to a static Constexpr option thing. And so now it's available at compile time, and it has a member size that I can, or well, capacity here, that I can assign to the capacity. So now I have both. I have my options and I have my capacity. Right? And it always works no matter what I got. All right, one more. In this one, I invent more concepts. So you really get to love concepts when you do these things because you can restrict, you can be very expressive, and you don't have any of the pre-C++ 20 blow up. So here I say exactly what I want in nicer terms. Right? So you can hide away the concept that has the full explanation. As long as you give it a decent name, everyone will probably roughly understand what it's doing. Plus, it doesn't matter anyway. It's a restriction that roughly says what it wants. And then in the actual code, you only have that concept. However, our auto parameter is not a type. It's an actual value. So therefore, I have to use decal type to get to the type. And then I can use that with the concept. All right, so then I can also make this a bit simpler. In this case, I can use an aggregate, so I don't even need to provide any constructor or copy constructor or anything. And I just do value assignment with braces, and that will work just fine. Okay, limited vector. Let's look at some of the implementation. So here's the access operator, square brackets, receives an integer. This one should have said Constexpr. No. All right. So why does it not say Constexpr? Because the first time I wrote this, the compiler was complaining. Why is it complaining? Because I wanted the checks, the assert here. And the compiler said, nah, assert doesn't work here. So, all right. Same then for the pushback. So no assert, we have to find something else. After long searching, I found that actually upside logging in Fatal perfectly works. It's amazingly Constexpr safe. I don't know how they do it, and I can't be bothered looking into this. But the compiler is happy, so am I. It's an assert that logs, and the compiler is happy to do this at Constexpr time. Still have no clue how it works or how, don't care. All right, so pushback. We also can't use new, or it's really hard to do. but there's an easier solution. You can do standard construct add, which is Constexpr safe. And anyway, we need a version where we already have the address because we know exactly where it goes. It goes into our array, into the data thing, and that's how we have the address. And then, well, this one is the move version. So we obviously have to forward because it's a R value expression, right? R value reference, to be precise. So of course, there's also a pushback, const reference, and then there's a popback, same story. Delete doesn't work. We need destroy add, same story. Constexpr safe version of this comes with C++20, so we can do this. All right. So then we get more and more and more of these functions. Here is size. Well, guess what? It returns the size value. Empty, size equals 0. Clear just goes over all of the elements and it does popback. So here's where we call our destructors, if we need them, if we want them. So then there's resize and reserve. My favorite actually is shrink to fit. Is an optional interface for vectors. Well, the documentation says it actually doesn't have to do anything. So yay, shrink to fit doesn't do anything. I can implement that function. All right, so constructor. First constructor is Constexpr, default constructor, no except, default. Now this thing is Constexpr safe, kind of. We still need to deal with these pesky destructors. So, first destructor, Constexpr destruct no expect requires a flex. So this is where the flex comes in. So this one says empty destructor. So we tell it to default. So what does that mean that I wrote this? Well, I have a container that may or may not have some elements stored, and I default the destructor of the whole container. So what happens when this thing terminates with this flag set? Well, nothing. No destructor is called. It calls its own constructor, which doesn't do anything because it's a union that the compiler thinks, well, it's probably a none, so nothing happens. So it actually doesn't do anything here. And the second version is the version with the flag not present, and that one calls clear. So then we call the destructors. And both of them can actually be Constexpr? No, because there were some requirements. So nothing can ever be easy with C++. So in order to make this Constexpr, we have to do is trivial destructible. But if we do this, oh yeah, this is one of my favorite things. And one of these million oversights, there is a concept destructible, but it is translating to is no throw destructible. I don't need this. I want is trivially destructible. Doesn't have a concept, so we have to write it all out. All right, so now I have a Constexpr destructor that can only handle trivially destructible elements. So I'm screwed if I have something more complex at runtime. So what do? Well, we just provide another one that has the opposite requirement. So we just invert the requirement. Now we have both, and now in this other constructor, destructor, we can remove the Constexpr, and now the compiler is happy in all conditions and compile time and runtime. So there we go. Limited vector, Constexpr safe, works at compile time, works at runtime, shares pretty much all of the C++20 interface. I couldn't be bothered yet to implement insert because there are too many versions of it. And yeah, it already has on the pro side some C++23 stuff, so it's a give or take. All right, next up, limited set and limited map. They are more or less the same. Why are they more or less the same? Think of what they do. They store some elements and they are sorted. In the set case, the key is the whole thing. And what happens in the map case? It's typically a pair and the key is only the first. So, well, if you think about it, as long as you can convince the thing that sometimes it looks at everything and sometimes only at first, it's the same, right? So all we have to do is we have to have a one implementation. This one here is called limited ordered, and it's hidden away because you should never work with it directly. And that implementation is told by its two using classes how to get to the key. And that's the whole difference of those two. And technically, there may or may be some differences in return values, but you can explain them in the exact same way. So it's all like a bit of template logic and handling the types correctly and letting the compiler on occasion convert some stuff. And because you get copy elision and all of these optimizations, it doesn't hurt, it doesn't translate to any runtime. And so the actual implementations for limited set and limited map are super, super boring because all they ever say is using limited order assign, using limited order iterator, using limited order, and you get the idea. It's like it has only using instructions, and that's the end of the story. So it just pulls in whatever is in the limited order. All right, so key map value and, well, compare. And I had to put the options somewhere, so my divergence is similar to the vector array case before. So the options, same thing. Here they take the size to limit. So we have continuous memory for our set or map, and we limit the size. And we have some options. Here there are a bit more. We see some of this later. All right, limited order. Let's look at how this is implemented. So this function here is one of the Constexpr constructors. This one takes iterators, first, last, has a compare function that you can give it, and it initializes the key comparison from that compare. So the higher up two containers, they have to make sure that the right comparison comes down here. But it's still default as a parameter. Right, so we still get the default, which translates to standard less for whatever the key type is. All right, and how does this work? Well, we just do a while loop until we reach the end that we specified, and we just place them, and that's the end of the story. So the work actually happens in place, and then in place, as you might guess, calls construct at and fills the elements we have from our uninitialized memory sketch space. All right. Here is another one, because I said flex. So here's a flag, require sorted input. Because we generate this stuff, why spend compile time all the time when this was already sorted up front anyway? So why spend ages sorting all of these in the compiler, which takes compile time? So I thought, like, that is stupid. I can do this. So here's a flag that just says, well, if this is set, then I know the input is sorted. I just do them one after the other. So we do the construct at directly as they come. They are sorted. Otherwise, we have to use place, which does the placement and movement and all of the shenanigans, which are silly to do in the compiler if you don't have to. All right. And so this goes on and on and on and on and on and on and on. Okay, so there's a lot about sorting. The interesting part is you can deal with all of the sorting requirements of these containers with two functions. All you have to implement is lower bound and upper bound. Everything else can be implemented in a way where it just calls those two. You don't have to do anything else if you don't want to. Lower bound and upper bound is enough. Now we have contiguous memory. That's awesome because then I can call standard lower bound and standard upper bound, which works perfectly fine for contiguous memory, and I'm already done with my implementation. The rest is just like pure mechanically calling those two functions in the right version. All right, but it's nice at compile time because at compile time it doesn't really matter that much. It's annoying at runtime because that's a slow implementation. All right, so index of. I said we have continuous memory because we have this array, so we can work with indices instead. So here's a version of index of that is working with lower bound and the key management. So I said all you have to do is call lower bound or upper bound depending on where you are, and you have to deal with the keys. So this is the version. Happily works, compile time, runtime. All right. Now we can restrict this with requirements, and we can say when exactly we want to use these things. And so suddenly you can use flags for further optimization. So here you can already guess there's a version that says I want to optimize this container for further stuff with loop unrolling and all of the funky stuff you may or may not be able to do. Well, there'll be some dragons. It's a bit longish to do because loop unrolling first takes, I think it's 20 lines of code I need for one loop. And the current implementation allows loop unrolling up to 32. So you would see 32 times the same code. Or my favorite, we can do it in less. We can do it in roughly 60 lines of codes because we can use macros. So we just define a macro for this thing and then call the macro 32 times. All right, so I'm not showing this. So that stuff, the limited order is about 1,000 lines of code. Much of this due to optimization. A lot of it actually purely mechanical because it needs to do all of this, iterator constructions, all of this kind of stuff. The set then comes in 300 lines. Roughly a third of this is nice ways of creating a limited set without you having to specify the size from various different things. If you read the code, it's hilarious once you hit strings and different versions of strings. You have to provide suddenly you get required lines anywhere, and then you get weird versions of these kind of things and how to decide them. So that's what you do with 100 lines. And the other 200 lines is the typical C++ bloat of include and what you have. And then using lines, roughly 100 lines of using lines to pull in the functionality. Limited map is just a bit more complicated. Same story there. All right, here's an example. So this is a simplified version of how we use this in production. So we run a template system called Marco, which basically allows you to program Python to create C code. So effectively what we do is we have our schema. We take the schema as input, we run Python, and it looks like some old kind of PHP or whatever CGI script, blah, 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 templating stuff. Looks exactly the same, only it's Python. And it spits out C++ code. And because here we know this stuff is sorted, well, technically we actually call the function sorted in Python at runtime when we once generate this. And we generate the code looks sucky, so then we run Clang format so that it looks always the same. And then we have a test that verifies that whatever you didn't end up modifying this and compares it to what actually is checked in. Why do we do it that way? Because if I were to actually take the code from this template generation, I would need to generate this all the time. That kind of violates the idea of speeding up the compile time. So I only do this when the input for the templates changes or the schema changes. And I use otherwise the checked-in version, which now allows me to cut the compile time down. Make sense? Right, and then because we force everyone to have decent formatting, we run Clang format. So I also need to run Clang format on the generated code. So the last step is generating and then comparing that is still the same. If it's different, well, whoever did the changes probably in the schema then has to update the actual submitted version of the file too. All right, so let's break this down a bit. We have here a line, static Constexpr inline. So this is somewhere in some other class in a header. And it's forced inline because if I don't write inline, then the compiler will tell me that the storage for this has to go somewhere. But I don't want the compiler to put the storage somewhere, or I don't want to tell the compiler where it goes because I say this is a const expression and the compiler should deal with it at compile time and figure out whatever the compiler wants to do. Maybe, ideally, there actually is nothing left of this container because every single function is const expression. So if we write the code correctly, there's nothing of the container at the end left. right? And yes, there is code where there's literally nothing left of all of these like 2,000 lines of code. All right, so at some point we have to, I said triplets, we have to create those triplets. So that's the line in the middle. And we obviously have a variable that's assigned to that we can later talk to. And then, so in this case, it's not a size because we knew it was sorted. So I give it actually the size. Size comes from the schema. And I give it the flag. And the flag here says it's already sorted. Don't worry about sorting this. And now here's how this looks in performance-wise. So this is the 32 unroll steps. And it is the index of function, because the index of function is used for most of the implementation as a fast, because this one allows to be faster than the lower bound and upper bound variant, and it compares the various forms. And you can very nicely see exactly where our breakpoint is, how long the optimizations for the unrolling is. And there's another thing, I probably should step down here. You can see the blue line uses standard length, that's the best one here. However, in the beginning, the unrolling in the simple cases, because it doesn't have to do anything, doesn't need to call any other function, that one will always be the fastest. The red one is a different form where it doesn't optimize the index of, so and that's faster. You can actually see that optimizing index of at some point no longer works out well. And then the top two lines, blue and red, they are for the good version where we actually find the element. And the other ones, the yellow and the green ones, are the ones where we don't find the element, so a miss. So, and why is this the yellow line much faster? Because it's much easier. There's no loop involved, no nothing. It's much easier for the program to find that there's no element. It just runs roughly 32 conditions, and then it's done. That's the end of the story. And the other implementation is much more involved, and that's why they are slower. Okay, so here is 24 unroll, and it shows you a bit like where these lines go. So that helps a bit deciding for a single processor, for a single condition, which variant you should do and how you should configure these. So there are differences. They really vary by actual use type. So in case this wasn't clear, so what we are measuring here is we have a container that was done at compile time, fully initialized, that's just there flat. And the only thing we are doing is now talking to it at runtime, even though the functions are Constexpr. We talk to it now at compiled at runtime, and we measure how fast they then are in runtime, because we want to know, is it actually worth doing this also at runtime, or can we only do this for something that's purely compile time? All right. So here's the next thing. Now you get a funky thing. You see this yellow line. This yellow line uses something compare less. So there's a new thing, the spaceship operator. Who's used the spaceship operator? Right? Do you guys like it? All right. I was actually hoping that maybe I can write a spaceship operator that is faster than standard less. Most of these slides where I compare them tell you, no, you can't. And that is because the spaceship operator has to do all of these comparisons and less doesn't. So technically, the spaceship operator always has to do more work. There's no way to convince the spaceship operator to optimize it. The only way how the spaceship operator in this setting is faster than standard less is if you do loop unrolling, and that's why the blue and red lines here are a bit higher at the end. So why are they better than their counterparts, even though they use this silly spaceship operator that is actually more work? So any idea? Why would they still be faster? No, this is all a silly thing. It has a lot of force inline experimentation going on. But yes, good idea. Could be a reason. Other ideas? You can rewrite the algorithm and build up on the knowledge that the spaceship operator has in addition to standard less, and that actually, if you construct the algorithm right, lets you write the same algorithm faster. But only for some conditions, and turns out only for the miss cases. As soon as you find your elements often enough, standard less is still faster. It's really annoying. So, failed experiment. This one is just, the next one, it's find. More of the same story. You see the exact same behavior. Well, we guessed that it's all based on the same implementation at the end of the day. So effectively, this is just another wrapper on top of what we've seen before. Now, here's my favorite. This is Apple Mac Studio M2, as expensive as you can buy. And holy moly, I cannot explain this. I've followed CPU design since I am, I don't know, like 16, where people basically didn't know what a CPU is. I know a lot of this. I've played with cache grind forever when I was a bit younger. I have no idea what Apple is doing there, but this is Apple. So obviously Apple does a very, very funky way how they handle their immediate caches, because you can see the spikes go on interesting numbers. So it clearly has something to do with how they organize their caches. So if you think about, mostly today we work with Intel and AMDs. They typically have 256-bit cache lines, bytes, cache lines. So you get like a whole chunk and you must deal with all of this chunk. So they have all of these prediction engines and out of order executions. Why? Because they anyway have to deal in 256 bytes. So they might as well see what they can do with them, because they always get 256 bytes, right? So that's why Intel and AMD are so complex. But Apple, with their M2, completely different architecture. They own everything, so they obviously found some interesting additional optimization ideas. And with that, that's the end of the presentation. If you have any questions, I'll try to answer them.